I'm Mikel. I lead Earth Genome, and yeah, I'm going to be looking at this developing technology, this technology stack, this ecosystem from the other end of things, really starting point with what impact is it having on urgent problems that we're having today. I don't know about you, but I'm impatient, and I think the world is speeding up. That's the best benefit of these technologies. We're able to move faster. And Earth Genome, which is the nonprofit that I'm part of, that I lead, is wholly focused on collaborating and partnering with people on the front lines who are trying to understand the impact that large scale human civilization is having on the world, as well as potential solutions to move to a more sustainable future. We feel it's really important for this kind of work to be done as a nonprofit. I was at a for-profit for years, led the community team at Mapbox. Fully think there's, especially in geospace, super important for people to be taking advantage of the market opportunities. But when it comes to the environment and with climate, there is a really critical need to be focused. And that's why and to have trusted relationships. And that's why we operate that way. But we don't operate as a traditional nonprofit. We move fast. We're a dozen people. We're very collaborative. We work in the open. We essentially operate as a tech startup. And we love technology. We love geospatial, front end, visualization, all the infrastructure and back end. And we especially love when we can apply the science, this data, and this knowledge in a way that is going to be useful for frontline defenders of our environment. And for many years, that's been, AI has been a top interest. One of the critical needs in the environment is to be able to find things, identify what's where and what's changing. And the way that we did that a few years ago, when Earth Genome built Global Plastics Watch, is a custom model. We assembled loads of data. We spent a lot of time, as the Clay slide showed. There was months and months spent by engineers training the model and doing something very custom just for that one specific purpose. And since 2022, as this idea of geospatial foundation models has really started to emerge, we're very intrigued about the opportunity to scale this up by using foundation models, which were trained once, but then quickly applied by utilizing embeddings. Could we solve these kinds of problems for search, but other problems as well in a much more efficient and fast way? Because we needed to address planetary change, we needed to also make sure the technology was operating at that scale. Since then, there has been a huge explosion of geospatial foundation models. This is a collection on GitHub of models. And it's amazing that there's been all this research, development of new models, new ways of working with different data sources. The conversation, thankfully, in the research space, particularly at the AGU conference in DC last month, has been turning to, so what? What do we do with these things? How can you actually apply them? There's been a lot of talk about the promise of what these things can do, about this sort of speed up and efficiency gain. And unfortunately, really, the risk of a trough of disappointment after a large hype cycle of what these models can do. So I think it's critically important as a space that we turn to thinking about products and thinking about applications. The main application that we've focused on so far is finding and monitoring things. And I'll talk about another project that's informed our trajectory in really grappling with foundation models and this technology and building product around them. And that's the problem of mining, gold mining in the Amazon. It's called artisanal mining, small scale mining. It makes it sound much more palatable than it really is. They're widespread, small mines, often made by locals to mine for gold, some often connected with criminal networks. And these are real challenge, and they're also in protected areas. They're in indigenous territories, and there's a lot of challenge if you're trying to identify them fast enough so that you can have a reaction and stop that mining before it starts. We have data, I'll show you, going back all the way to 7 years. But really what's most important is finding the mine that's happening this month so it doesn't spread and you can actually stop it, have enforcement action. These are very fast moving. They can evolve in a matter of weeks and start up. We're talking about the Amazon here, so cloud cover is a real challenge to get a clear view of things. And it's hard to distinguish. There's a lot of drivers of deforestation in the Amazon, from agriculture, from harvesting of trees, just increase of infrastructure. And so you also, if you're really just focused particularly on this activity, you have to differentiate. This is an animation from the Amazon Mining Watch website showing the evolution of a mining site in Peru, I believe. And you can see it starts off to very small, but it can grow. This is from a trip that Dr. Ben Strong on my team took a few months ago to this very location. And you can actually see the footprint on the ground. It really does have a major scar on the landscape, this activity, as they're sort of sifting through the sand in order to find bits of gold. So what did we do? We did the classic approach here, the custom model, assembled lots of Sentinel-2 imagery, hand labeled both positive and negative examples across the basin, applied the AI, machine learning, to do detections. And actually, it turns out to be a really tractable problem. And Amazon Mining Watch, our detector, is really good at finding these particular activities. And that has led to responses. Folks on the ground like Gustavo with Instituto Socioambiental use this as key information in their work with indigenous groups, with governments, in order to have action happen. And that has happened at official levels as well, with the national police in Brazil using Amazon Mining Watch data as part of cases made against illegal mining. It's still not it's fortunately, this kind of activity is slowing down and enforcement is stepping up, but it's still a growing problem. So what if you want to modify this model a little bit? What if you want to, rather than detecting mines, you want to detect other disturbances in the Amazon, like illegal airstrips? We have built a model, a hot dog, not a hot dog model, mine, not a mine model. And it's very single purpose. And so if we wanted to find something a little bit different, or even something a little bit adjacent to artisanal mining, like there's riverine mining as well, how you have to basically start from scratch, assemble imagery, get more training data, retrain that model. This is the case for foundation models. Can anyone easily make their own Amazon Mining Watch? That's sort of the challenge that we've given to ourselves. You've seen similar images. That was great to see that in the 51 product. This is showing geospatial tiles in embedding space and showing natural clustering that happens when this is of course reducing that high dimensionality to just 2 dimensions. But you can see naturally there's clusters there of chicken CAFOs. This is the state of Alabama, and there's the transformation in embedding space, and then naturally things cluster together. So there's something to take advantage of in the data, of course, and find things which are similar to other things. That's the idea that's led us to build Earth Index since 2022. The idea is to build a product, an interface, an application that doesn't require someone to come in with knowledge of how to assemble all this geospatial data or the details of how machine learning works. They have to have knowledge of a problem, knowledge of an area. But from there, it's as simple as interacting, applying a few labels, and iteratively exploring what the similarity search through the foundation model to identify and build up really strong data sets of the things that you're searching for. And this process can be really fast. It doesn't, within hours rather than months of effort, you can get something really, really good. And it's involves a human in a loop, and that human is an expert on the end problem, not an expert on the technology. This is, I'll play the video to kind of show how it works. You have a user account. You come in, create a new project, give it a name. Currently in Earth Index, we have a number of set regions that have already been indexed. We're moving to global very soon, but here we're selecting Cambodia and a set time period. And then interactively, you go into the application. You label examples. Here we're looking at solar panels in Cambodia. Apply just a handful of labels. Here just a half dozen. Query the back end to find similar essentially embeddings which are similar to those. And then it returns the results that you can then explore. You can filter by different confidence levels. And then you'll see the demo kind of goes through and shows some of the results, or is able to pick up other installations of solar across the entire country just in a matter of seconds. And so pretty soon you'll be able to do this in any arbitrary location around the world, and basically bring your knowledge in order to find and build a data set. Since I think this is a somewhat technical audience, I'll just go a little bit into how we assemble the kind of the components to make this happen. First, you need imagery. And we largely work with Sentinel-2 imagery. We need cloud-free data, so that means we need to composite over a time period. So we have a method of selection which tries to use the smallest number of images possible to speed up processing. We quickly we enhance cloud mass in some very kind of simple rubric ways. Apply that to the imagery. And we've really focused on making this efficient on AWS infrastructure. So we're using ARM processors, which is a big cost reduction, code improvements by using certain optimizations in Google and other libraries. And we're just fine-tuning the results of our 2024 composite, which are going to be posted on Source Co-op next week, which is a way for to distribute open data sets in a cloud native format to anyone. And the thing we're really proud of is how efficient we've gotten this. And we're talking hundreds of dollars now to do a global composite. We have a lot to thank with the efficiencies which are coming into cloud infrastructure. But it's also, we're a nonprofit. We want to be very careful with the money that's coming in, that our donors are giving us, very considerate of it. So we're now in a position where we can run repeatedly. We're moving towards quarterly basis in a very, very cost efficient manner. We then need to tile up that imagery, and we use the Lambda functions with some code written around Rastrio on the back end. We pre-cache images to Zoom 11, and then we have on-demand production and caching through Lambda and CloudFront. Then we need a grid. We need to divide up the world into squares that we're going to run through the foundation model, generate embeddings, and load into our database. We've used several different gridding systems, and most recently we've settled on the major Tom gridding system was developed at ESA, and the real advantage of this gridding system is there's a couple you can get more or less similar size chips tiles globally, and you can also scale it up to whatever resolution is relevant. We have our tiles, our chips at a few hundred meters square. So this has proven really useful. You can also use, there's also ways of using the identifiers very easily sort of to go back and forth between the geographic coordinates and the gridding system. And to use those, we use a lot of Go for developing our APIs and Python for processing data. So we wrote a library in Go and a library in Python to generate major Tom grids, and both of those have been released open source. You can find those on our GitHub. Then the heart of it really is then the embeddings generation, running each of those, few hundred meter square chips through foundation model, getting our vector embeddings. So we've been for many years using the GULab model. They're out of the Technical University of Munich, I think very unpretentiously doing very core work on geospatial foundation models for years. The SoftCon pre-trained model has proven really effective for our use case and fast as well. Once we have the embeddings, we've set up a database using Postgres, PostGIS, PG Vector, which has been just continually improving. Seems like every month there's some new functionality or new efficiency. So we've been really happy with that. We also use Postgres for managing like application state and the user account stuff as well in a separate database. With Input API on top of that back end to do querying of those embeddings and do similarity search. We have endpoints again for like project management, application management. We have to have multiple tile endpoints to load all of the vector and raster data in the front end. And then we use Stack, and we use some third-party services for authentication, like Clerk. On the front end, we have an Next.js application using Mapbox GLJS in the UI, and that takes care of all the sign-in and project management, AOI selection, labeling that whole experience that you saw in the video. Okay, I said this was going to be about so what. So what? A couple examples of results that have been in motion over the past year and showing just the value of this approach. We're part of the Climate Trace Coalition, really great project. We do all the data infrastructure and design and build the front end. And the goal of Climate Trace is to do greenhouse gas emissions for very small scale, every individual facility and asset around the world. And because that's actionable, you actually can know, in this case, an individual cattle feeding operation, how much methane is being emitted from that farm. Globally, cattle operations account for a huge percentage of emissions. 14.5% of global greenhouse gas emissions can be attributed to cattle operations, and they're often and that's due to burping and pooping. That's what's creating all that methane. A huge majority of cattle around the world are in large-scale facilities. They don't always look like this, but it's often more concentrated operations. And there is no global database of where these all exist. Even in the United States, it's very much a state-by-state affair. Some states have pretty good data of where all these operations are. Some states have nothing. So it's very hit or miss. And what you need to do emissions modeling is find the locations, get a kind of a rough estimate of the footprint, the size of that area, and then use a rough method to convert to head of cattle, which you can then use to convert to amount of methane per year. Part of the challenge with doing this globally is these facilities look really different in different parts of the world. Even across the United States, if you were going to do a specially trained model, you would need to retrain it for different regions of the US, let alone going to China or Brazil or France and Germany. The footprint of those, while there's some similarity in terms of structures, is different enough that these do occupy kind of distinct areas of the embedding space. And so there's a need to apply local knowledge of what these facilities look like in these places in order to actually build that database up. And it's been very successful. This is a work in progress. This is the release of data from November 2024, but we're well on our way to collecting all of these locations around the world. And it's done in a way that is driven by, by interaction, by human in the loop, non-machine learning experts finding these places at scale. Okay, that was example number one. Example number two are airstrips in the Amazon. Referred to these before. There are many places across the Amazon that are involved in the distribution of narcotics, and to get those get that out, often will be airstrips built in the middle of the Amazon, um, sometimes in protected areas or indigenous areas, and not only do these have an impact on the local environment, they also have a really strong impact on the community. Obviously, this can be dangerous for local people, and so it's a real scourge and a real problem in places that are extremely isolated from the rest of the world. Here's like some examples of what they look like. They can be built relatively quickly. This kind of linear clearance. It's just kind of in the middle of the forest, and they can also just be used for a very short time. One of the interesting challenges about finding these is that if you look at part of it, it looks very similar to a road, and so there's a lot of when we did a lot of the labeling in order to find these things, we really focused on the ends because that's a very distinctive part of these kind of features, is that they're short and they actually like end, and then beyond the end of the airstrip, there's Amazon jungle. We were able to, by the way, important, we did this work in collaboration with Mongabay, which is an incredible environmental news reporting entity, and they needed this information where these airstrips were so that they could then do on-the-ground reporting to understand what was the real impact of what was happening around these airstrips and get a big picture of the environmental community impact. We found 67, which had previously been unknown, and 30 of them were actually within indigenous territories, 26 of them near them. So this is very fresh. This was reporting in collaboration that was released in November, and developing story and developing action. So to conclude, let me just give you a picture of where we're going next with Earth Index. Like I said, global coverage is what we're 100% focused on right now. So later this quarter, anyone will be able to come, sign up, choose an area of interest anywhere in the world, do a search, and find things which are relevant for them. We're very excited about what kind of potential that opens up and to see what people do with this technology. We've been working on annual data. We want to move to quarterly. So there's a lot of data infrastructure work that we need to do to make sure, and also get even more clever about how we handle generating cloud-free imagery. And we're doing research into utilization of other modes, both high resolution imagery. We're working with planet imagery in a number of places, and also SAR, using radar data. This is going to be really a critical part, in combination to find other kinds of activity that just Sentinel-2 imagery alone has not been able to do. Following that, we're looking at allowing within the application to do kind of lightweight ML models, lightweight training heads on top of the embedding, so that you can work at a larger scale than just the interactive approach. Setting up systems to do repeated change detection over time and to set out alerts when something new is found. And we're very interested in new applications, so that we've been very focused on finding, monitoring, but categorization is coming up a lot in topics related to biodiversity. So we're interested to see what can be done there on a comprehensive scale. And we're also very interested in how these other models apply. Like we have largely used the GLab models, but very interested in how they compare, and see Earth Index being totally an application layer. We feel like it can be kind of the battleground for see how different models, what strengths and how they compare against each other in different circumstances. And so we're very interested to try those out as well. Great supporters and great partners. So thanks to them. And before I conclude, let me just say a final pullback note. As a nonprofit operating openly and really focused on the environment, this is our vision for this infrastructure around foundation models and Earth observation, particularly is really to focus on open sharing assets. We don't if something gets processed, it shouldn't and you can share it so that you've saved time for someone else. That's why we share those imagery composites. We've been making embeddings collections available in GeoParquet on Source Co-op and working on the standards in order to encode necessary information about generation of those embeddings. We think it's super important to share knowledge. That's part of why I'm kind of talking to you all. We blog a lot about like our process and how we actually do things, and share code so that there's efficient processing so that everything can speed up. And particularly, again, for these impactful use cases for the Earth, critical use for the environment, the infrastructure, those APIs, we think it's really important to prioritize access to those folks who are on the front lines and make sure that that sector is not hindered by proprietary and commercial activities, which I love, which is great. And there's so many problems to solve in this space. But when it comes to the fundamentals of this planet, I think we need to prioritize making sure we need to have these tools in people's hands. Just full stop. There's my contacts, and if there's a link, earthindex.ai. You can go there and you can sign up for our alpha and waitlist, and then we'll add you as we kind of roll things out, and particularly when global comes pretty soon. That is the end of my slides. Jimmy.